And we are rolling. Okay. Just have to double check. Yes. Okay. Yeah. Okay. So. So generally, in the presence of degeneracy, remember that same energy for different states, multiple states having the same energy. What we're interested in isn't so much the probabilities of two different states, it's the probability of the atom having two different energies, whatever state it's in having that energies, one of those energies. So generally in the presence of degeneracy, we're interested in the relative populations of different energy levels as opposed to different states comprising a different energy level, a given energy level. We are interested in the relative populations of different energy levels as opposed to the different states comprising a given energy level. So for example, in hydrogen, all the n equals 2 states have the same energy. So we don't care what fraction are in n equals 2, L equals 1, m sub L equals minus 1, m sub s equals plus 1/2. We're more interested in how many of them are in n equals 2, period. We don't care about the other quantum numbers. So let's make that official. For example, we will be more interested in the probability of an H atom having n equals 2, say, versus n equals 1, without caring about the values of L, m sub L, and m sub s. Because the thermodynamics only cares about the energy, it doesn't care about anything but the energy when we look at the ratio here. So now we're going to write the Boltzmann equation. In this case, the ratio of the probabilities of occupancy and thus also of the number of atoms in each level. We have some big sample of them. Is probability of energy B divided by the probability of energy A, which will be also the same thing as the ratio of the number of atoms in level B, energy B, divided by the number of atoms in energy level A. We have what we had before, except now we have to multiply by what we call the degeneracies, the number of different states that have the same energy. So we get G sub B, which is the number of states having energy B, times e to the minus EB over KT. Because they all have the same probability as one another, since only the energy matters, divided by G sub A, e to the minus EA over KT. Or in other words, it's GB over GA times that same exponential, e to the minus EB minus EA over KT. And this beast is the Boltzmann equation. I'm just writing it on top because I'm out of room. So important that it deserves a box. And as we mentioned, GB and GA are the degeneracies of levels EB and EB and EA. And we should probably write down that N, B, and A are the number of atoms in each state. So here's where I say, of course, what questions do you have? So far, so good. Okay? All right? In that case, it's time to do example 8.1.3 from the book. 8.1.3. Yep. In which we answer the following question. For a gas of neutral hydrogen atoms, at what temperature will equal numbers have atoms in n equals 1 and n equals 2?
For what temperature?
For what temperature? Yes. So for a gas of neutral H atoms,
Oh, so they're asking like what energy levels, the n sub b will equal n sub a?
For n equals 2 and n equals 1. So in other words, for what value of t will n sub 2 over n sub 1 be 1?
Yeah.
So we're going to set 1 equals g sub 2 over g sub 1, e to the minus energy difference over kt, and solve for t. In other words. Yep. And what, for a gas and neutral hydrogen, at what temperature will equal numbers have electrons in n equals 1 and n equals 2. So in other words, we want the condition where if we go back to Goldilocks and the 3 stars, we want the condition where these two populations are equal to one another. There's just as many with the electrons sitting at n equals 2 as in n equals 1. And these are for the neutral atoms. Right, so we're not accounting for the ionized ones here. This isn't accounting for ionization. This is saying, of the atoms that are neutral, what fraction will have n equals 2 versus what fraction will have n equals 1, and what temperature will those be equal to one another. We'll find it's much higher than 10,000 Kelvin. Which by itself would say, oh, that would be even better for making hydrogen lines, but, you know, spoiler alert, at that temperature the hydrogen is almost entirely ionized. There essentially wouldn't be any neutral hydrogen atoms at that point.
Yeah, because that thing,
Because that's shot way up above
goes
10,000
up.
Kelvin. So that's the spoiler alert. We're pretending we don't know that yet. So remember, we had mentioned this the other day. G sub n is 2n squared. So G sub 1 is 2 because in the ground state, you can only have spin up and spin down, that's it. L has to be 0, m sub L has to be 0. And G2 is 8.
Because we have 3 point values for L, m sub L, for m sub S.
Right, and then so there's L equals 0 has just ML is 0, m sub S is plus or minus F, so that's 2 states.
And
Then L equals 1 has m sub L could be minus 1, 0, or 1, each of which comes with 2 states, so that's 6 more states for a grand total of 8 states that can correspond to n equals 2. The other thing we want to remember is that as we deduce from the Bohr model, and Schrodinger agrees with this, the energy of state of the state with principal quantum number n is minus 13.6 electron volts over n squared. So as we've already mentioned, E1, the energy of the ground state, is minus 13.6 electron volts. And E2 is 1/4 of that, minus 13.6 eV over 2 squared, because that is 2, that's minus 3.4 electron volts. So now we plug into our equation. The Boltzmann equation says N2 divided by N1 is G2 divided by G1 times e to the minus G2 minus E1 over KT. And we know what G1 and G2 are, so that ratio is 4, 8 over 2. And we know that E2 minus E1 is 10.2 electron volts, so e to the minus 10.2 electron volts over KT. So let's make the ratio 1 and solve for T. So 1 equals 4 blah. So therefore, e to the plus 10.2 EV over KT is equal to 4. I got that by saying 1/4 is e to the minus that, and then if you take reciprocals, 4 is e to the plus that.
Then we take the natural log.
Yep, 2, 4, 6, 8 times 2 natural logarithm. Yeah. So 10.2 EV over KT equals log 4, natural log of 4, and so therefore T is equal to 10.2 EV over K natural log of 4. This is where it's convenient that we put K in terms of EV per Kelvin. So this gives 10.2 EV over 8.62 times 10 to the minus 5 EV per Kelvin times the natural logarithm of 4. Throw that into mathematic or your calculator, and the result is 86,400 Kelvin. Yeah, so toasty. Gotta get quite toasty to get that significant a number equals 2.
I was not expecting that. I thought like maybe 20,000 or 40,000.
Way higher than that. Way higher than that.
That's the number of seconds in a day.
It is, isn't it? Yeah. It is, isn't it? I just never noticed that before. Wow, that must be some profound connection in the universe. Or not.
Or not.
Right. So this takes us back to that plot that we were talking about. Notice that's not even on the scale, because in this condition, if N1 and N2 are equal to one another, this would have to be 1/2, right? And notice at 25,000 Kelvin, we're only up to not even 0.04 yet. So it's way up there somewhere that we finally get to this point, which is why they didn't even bother. Right. And notice at 10,000 Kelvin how tiny the fraction is. We already looked ahead and said 10,000 Kelvin is where I get strongest hydrogen lines. That number is extremely tiny. Only a tiny fraction of the hydrogen atoms are at N equals 2 at the ideal temperature of about 10,000 Kelvin for making hydrogen lines. So
this value of 1 for the ratio is theoretical, right?
it's theoretical, yeah. It's completely unrealistic because at this temperature there'd be virtually nothing in the way of neutral be described by this. Yeah. The fraction of neutral hydrogen atoms would be so tiny as to be negligible.
Wow. Can you produce temperature to that scale? Like, would it be possible to produce?
You can, but if you had a bunch of hydrogen gas that you heated to that temperature, it would just be completely ionized. Certainly the sun, there's a layer within the sun that is at this temperature, but the hydrogen's completely ionized. Yeah. Mm-hmm. So, at 10,000 Kelvin, a very tiny fraction of H atoms have n equals 2. And for the sun, it's 5,800 Kelvin, it's even worse, right?
Yeah. That's why it's so weak.
Mm-hmm.
Like the intensity of the hydrogen structure.
Yep. So that's why the sun has weak hydrogen lines, even though hydrogen is very abundant. Sun has weak Balmer lines despite the high abundance of hydrogen. And so even though we've said it, I'll still just, officially write all this out. So, Balmer lines reach their maximum strength in spectral type A0 stars at a temperature, it's close to 10,000, it's actually 9,520 Kelvin is what is our real. And so we'll ask ourselves, why aren't they stronger and hotter stars if a bigger fraction of the hydrogen is n equals 2? And the answer is ionization. So, TEF for those stars, remember the effective temperature is the temperature of a black body would have the same flux as the actual star does. TEF is 9520 Kelvin for those stars. Why aren't they stronger and hotter stars, which have a higher fraction of their neutral hydrogen atoms in the n equals 2 level? Higher fraction of their neutral H atoms in n equals 2. And of course, we've already given the spoiler alert that it's because of ionization. So now we're gonna have to write down, after talking about it for a while, what we call the Saha equation, which describes the population of different ionization states. So,
The other side of the,
what's that?
the other side of the.
The other side of the coin, the one that does that. Yep. So, the reason is ionization. As heat increases, interatomic collisions become increasingly violent. Everything's moving faster. And also remember that as the temperature increases, the photons are more energetic too. And the photons interacting with atoms become more energetic. Causing more atoms to be ionized. So what we're going to do now is define what we call the ionization energy. And we have to be careful because, for example, if we're talking about hydrogen, there's no one energy that ionizes hydrogen, because if you're in the ground state, you need at least 13.6 electron volts, but if you're already in n equals 2, you don't need 13.6 eV, you only need 10.2, and if you're in n equals 3, you only need 12.1, so there's no such thing as the energy it takes to ionize the atom. So we have to be specific and say the ionization energy is what it takes to ionize an atom in the ground state, to strip one more electron off an atom in the ground state of the given level. So in other words, for the neutral atom, it's remove the least tightly bound electron from the atom when they're all in their lowest possible energy. For triply ionized carbon, it means put all the electrons in the lowest possible energy configuration for triply ionized carbon. How much energy does it take to remove one more electron as a minimum, the least tightly bound electron from the ground state of triply ionized carbon, and so forth. And then you have to account for the presence of other states using what's called the partition function. So, define the ionization energy, we're going to call that Greek letter chi sub I. So that's not an X, it's a chi. Small chi, not a big chi. Where I indicates the number of electrons that have already been removed. So not a Roman numeral, now we're being sensible. So if I is 3 electrons have already been removed, and the Roman numeral is 4. Because we're so. And we describe that given number of electrons having been removed ionization stage. So 2 electrons having been removed versus 3 versus 4 and so forth. Those are the different ionization stages. To be the energy needed to go from the ground state of ionization stage I to the ground state of ionization stage I plus 1. So if I'm got triply ionized carbon, its ionization energy is how much it takes to strip off 1 electron and leave behind quadruply ionized carbon, where that's also still in the ground state. Take the ground state of triply ionized carbon and turn it into the ground state of quadruply ionized carbon, for example. So to go from the ground state of ionization stage I to the ground state of stage I plus 1. So that's generally going to mean pull off the outermost electron, the one that's held least tightly. Because if you pull out an inner electron, that won't be the ground state of the resulting atom, because another electron can then drop down into the empty level, for example.
We can only remove the balance electron.
You could remove a more deeply bound one, but that's a lot harder to do. It takes a lot
Because
of
of
energy. Yeah, because they are held much more tightly. There's not as much
Being
screening
closer.
between them and the nucleus. They're closer to the nucleus and all that kind of
These
stuff.
electrostatic forces.
Yes.
Wow.
Yeah.
Everything works together.
Now, of course, like we just said, but you could ionize it in lots of ways. You're not necessarily going from the ground state to the ground state. You could pull out an inner shell electron. You can still do that. So, to account for the fact that the initial and final states won't necessarily be the ground states, we need what's called the partition function. And when you take statistical physics, you will have partition functions coming out of your ears. But the good news is you'll have already seen it before. Even though, we're not going to derive it there, you'll actually see, where it comes from. And it's usually given the symbol capital Z. And it's defined to be the sum from I equals 1 to infinity of G sub j e to the minus e sub j minus e sub 1 over kt. Where E1 is the ground state energy. And so if we like break this apart because, in other words, when I is equal to 1, E sub j is also E sub 1, and this becomes e to the minus 0 over kt, which of course is just 1.
Yeah.
So the first term is g sub 1 alone. So we can break it into g sub 1 plus the sum for all the other states, 2 to infinity of gj e to the minus ej minus e1 over k times t. Sometimes it's useful to break off the g1 there. Often g1 is the most important contribution because of the way that this exponentially decays as the energy increases. What questions do you have?
Just one. Is the index of underneath the summation is I the operator?
Oh, sorry, it's supposed to be j.
Okay. Yeah, just wanted to be sure.
Yeah, absolutely. Yeah, it's supposed to be j. Would make sense to sum over I and then call it j inside the summation.
I was trying to remember all the linear and abstract.
Yeah, you can't sum over an index that doesn't appear.
Yeah,
Yes.
because there are index in here.
Yeah, that made no sense whatsoever. I was even thinking as I wrote it, be careful. Well, you know what happened is it's wrong in my notes and I never fixed it.
I do it too. I just like I'm going through my proof and I'm like, oh, why have I summed over this?
Right.
Where is this?
I knew what I meant, you know, yeah. Now, you might not notice it at first, but there is a little problem here in that Z generally diverges. It's infinite.
Oh, it's an infinity.
Yeah, so we have to talk about why in practice we don't need to worry about that problem. In general, Z diverges, and we consider hydrogen as an example. As j goes to infinity, g sub j is 2j squared. We're using j for what we used n for before. Z is 2j squared, goes to infinity. But E sub j minus E sub 1 approaches 13.6 electron volts as a limit. As j goes to infinity, that energy difference goes to 13.6 eV.